Next question. Is f of x equal to the absolute value of x is continuous and differentiable at x is equal to 0? Okay, so let's start with the continuity test. So the first one is the f of c. So since our c here is equal to 0, so the f of c, f of 0 is equal to the absolute value of 0, which is equal to 0. How about the limit? So the limit of f of x as x approaches 0 is equal to the limit of absolute value of 0 as x approaches 0, which is equal to 0 as well. So the f of c is equal to 0, which is equal to the limit of the function. Therefore, the function is continuous at x is equal to 0. We expect this because according to our theorem um, that the absolute value function is continuous everywhere. So we expect that the function is continuous at x is equal to 0. Checked, but how about the differentiability? Okay, let's get the derivative of the function or the absolute value function. So the absolute value function here is absolute value of x, so f prime of x is equal to the limit of the absolute value of x plus h minus the absolute value of x all over h. So absolute value of x minus the absolute value of x is 0. So what remains here is the absolute value of h over h. Now take note, absolute value function is defined differently to the left and right of 0. It means that it has a different value of the derivative from the left side and also from the different derivative value from the right side. So in order to identify that, we need to take the real value inside the absolute value. So it means that the real value of h inside the absolute value bars, if our h is lesser than 0, the real value of h is a negative value. While for the h is from the right side, the h here is greater than the value of 0. Therefore, the true value inside the absolute value bars means that it is also positive, the positive h. Now let's go back to the left side. So the f prime of x is equal to the limit of the absolute value of h over h as h approaches 0. Again, from the left side, the real value of the h inside the absolute value is negative h. So negative h over h is actually negative 1. So the derivative from the left side of the function at x is equal to 0 is actually negative 1. And for the right side, the limit of absolute value of h as over h as h approaches 0, the real value of h is positive 1. So thus, h over h are equal to 1. So the limit of 1 is equal to 1. Notice that the derivative from the left side is different from the derivative from the right side. So it means that the real derivative at x is equal to 0 doesn't exist, since the one-sided limits do not coincide. Again, we can verify that by looking at the graph of a function. At x is equal to 0, we can see that our function is continuous, but it's not differentiable. We can see another sharp corner exists at x is equal to 0, producing different value of the derivative from the left side and the value of the derivative from the right side of the function. So again, the function is not differentiable at x is equal to 0 for our given function, absolute value of x. Here are the things that we need to remember, that according to the theorem, if a function f is differentiable at a point A, then f is continuous at A. So the limit of f of x as h approaches A is equal to f of A, or that's equivalent to the limit of f of A plus h as h approaches 0 is equal to the f of A. So once again, if our function is differentiable, then it is also continuous at that point. However, we need to take note of this following remark, that if our function is continuous at x is equal to a, it doesn't mean that the function is differentiable at x is equal to a. So it means that it could be differentiable, it could not or not if the function is continuous at x is equal to a. The second point here, if the function is continuous at x is equal to a, then the function is not differentiable at x is equal to a. That also means that if our function is discontinuous at that point, automatically we could conclude that it's not differentiable at that point. The third one is, if the function is not differentiable at x is equal to a, it doesn't mean that f is not continuous at x is equal to a. Again, if our function is not differentiable, it could be that our function could be continuous at that point or not. We don't know until we solve it. Further things to remember, if function f is not differentiable at x is equal to a, if one of the following is true, our function is not continuous at that point. The graph of a function has a vertical tangent line at x is equal to a, and the graph of the function has a sharp corner or cusp at x is equal to a. We have seen this through our examples previously.